Good morning, and thank you for the kind introduction. So I would also like to thank the organizers for this opportunity to explain my work here. And today I'm going to talk about several ingredients and methodologies for the large-scale topology optimization of the structures using adaptive mesh refinement techniques. This is a joint work between several people. Some of them work at our research group at the Technical University of Catalonia and the International Center for Numerical Methods in Engineering. So these are Ramon Codina, Camilo Bayona, and Sergio Idelson. And then Jesus Martinez and David Herrero work at the Technical University of Cartagena. Fermín Otero is currently working at INEGI in Porto, and Alex Ferrer is doing a postdoc in Paris. So the motivation for this work is that, with the growth of 3D printing in the last decade, mechanical elements with complex topologies can be manufactured, which could not be manufactured with previously molding capabilities. So in structural engineering, this allows to optimize topology with respect to structural needs, but at the same time, if the loading case is complex, this involves a lot of computational effort. So for instance, if we have fluid structure interaction, or if we have random loads or stochastic loads, then we will need to take this into account, and the computational cost of these simulations is going to be very large. Okay? So our objectives here were to develop a set of tools which allow us to deal with this type of problems. And in order to do this, what we did was to rely on mainly three ingredients. The first one is the usage of high-performance computing facilities and parallel computation. The second one is adaptive mesh refinement, which will allow us to focus the computational power in the regions where it is required. And finally, I will briefly talk also about reduced order modeling, the usage of reduced order models in the iterative optimization process. So our starting point is a parallel object-oriented multiphysics finite element code, which is coded in the Fortran 2008 standard. And well, with it, we can do nice, scalable, parallel adaptive simulations, which scale well up to thousands of processors. So here you have a simulation of the aeroacoustics of the human voice, which was run in 256 processors. And the kind of adaptive mesh refinement that we do is this refinement here. So it is isotropic adaptive mesh refinement with hanging nodes. But we can refine and unrefine, and we have good scalability up to thousands of processors. So today I'm going to talk about three ingredients that we are using, and the first one is going to be a variational multiscale-based error estimator for solid mechanics, which will allow us to refine appropriately our mesh. The second one is a set of strategies for the topology optimization under uncertainties by using high-performance computing clusters. And finally, I will briefly discuss some developments that we have been doing in variational multiscale reduced order models for the approximation of fluid structure interaction problems. So let me start with this variational multiscale-based error estimator. And the objective in this case is to obtain an error estimator which is based on the variational multiscale method and which allows us to solve solid mechanics problems. And of course, it should allow us to focus the computational power in the area where it is required. And we want to apply this error estimator to both linear and nonlinear problems. So we are going to also deal with damage mechanics and to 2D and 3D settings. And of course, this error estimator needs to be suitable to be used in a parallel environment, in a distributed parallel environment. So let me start with the finite element formulation. For our solid mechanics finite element formulation, we are going to use a mixed displacement pressure formulation. So both the displacement and the pressure are going to be unknowns of our problem. And then if we do this, the pressure is going to represent the hydrostatic part of the stresses. So if this is our momentum equation here, and these are the stresses are going to be decomposed into the volumetric part, which is represented by the pressure, and the deviatoric part, which is going to be represented by this constitutive tensor, the deviatoric constitutive tensor times the strains. Okay? And this is the constitutive equation for the deviatoric part, and for the volumetric part, we have the constitutive equation for the pressure. So this is the final strong form of the problem, this equation here, in which we have the momentum equation, which involves both this deviatoric part of the stresses and the gradient of the pressure, and then we have the constitutive equation for the pressure here. The nice thing about this formulation is that it is suitable for incompressible materials, so it allows us to effectively reach the incompressible limit. So now we take the Galerkin weak form, so we pre-multiply by the test functions both for the displacement and for the pressure, and then we integrate over the computational domain, and we obtain this Galerkin weak form. The issue with this Galerkin weak form is that, as it is well known, it is unstable for the incompressible limit if we use arbitrary interpolation spaces for the displacement and the pressure. And then what we are going to do is to use a variational multiscale formulation which will serve two purposes. The first one is precisely to stabilize this Galerkin weak form and to allow us to reach the incompressible limit. And the second one is to provide us with a reliable error estimator for the adaptive refinement process. So the idea of the variational multiscale method, as it is well known, consists precisely in splitting the exact solution of the problem. So this is the exact displacement and the exact pressure, and we are going to split it into the finite element part, the part which can be captured by the finite element space, plus the subscales. And these subscales here are going to be modeled. We are not going to resolve for them. We are going to build a model for them, but they will provide these two ingredients, which are a stabilization mechanism and an error estimator. The particularity of the variational multiscale method that we are using in our group is that we use a variational multiscale method in which we force that the subscales must belong to a space which is orthogonal to the finite element space. So we force our subscales to live in this space here, which is precisely the orthogonal space to the displacement finite element space and to the pressure finite element space. So if we apply this decomposition to the weak form of the problem, we obtain this weak form here, in which the terms which are not highlighted are the Galerkin original terms, but now we have additional terms, which are these terms in brown here are the terms which correspond to the displacement subscales, and then the terms in green here are the terms which correspond to the pressure subscales. So now, in this formulation here, we do not want to deal with the gradients of the subscales because we do not want to model that. So what we do is we integrate by parts the displacement subscales. And if we do that, we arrive to this expression here in which we have the brown terms here, which are terms which are integrated over the volume of our domain, so in the interior of the elements. And then we have these blue terms here, which are the terms which are integrated over the boundaries of the elements. So usually these blue terms here are discarded, but in our model we are going to keep them because they are going to provide an important part of our error estimator. So in order to deal with this, we are going to work with a split definition of the displacement subscales. So the displacement subscales are going to consist in the addition of interior or subscales on the element interior function, which is a bubble function which is going to vanish on the boundaries of the elements. And then we are going to have the second component of the subscales, which are the subscales on the element boundaries, which precisely are going to be defined on the boundaries, and they are going to vanish on the element interiors. So now we need to provide a model for all of these subscales, and in order to do this, we are going to start by focusing on the subscales on the element interiors, and in order to obtain this model, we are going to simply take our Galerkin weak form, and we are going to test this Galerkin weak form against the test functions not in the finite element space, but in the space for the subscales. And we are going to do this both for the displacement subscales in the element interiors and for the pressure subscales. If we work a bit with this expression here, and we diagonalize some of these operators by means of a matrix of stabilization parameters, we arrive to this final expression for the subscales on the element interiors, displacement subscales on the element interior. So in this case, they are expressed as the product of this stabilization parameter times the projection onto the space of displacement subscales of the residual of the momentum equation, and the same for the pressure subscales. We have this product of this stabilization parameter here times the projection onto the space of pressure subscales of the residual of the constitutive equation. And the important point here is that we, in our group, we are using a particular version of this projection operator, which is the orthogonal projection operator. So this is a projection onto the orthogonal space, which can be computed simply by using the identity projection minus the projection onto the space of finite elements. And these are the expressions for these stabilization parameters, which are in fact a diagonal approximation to some of the operators that we see up here. And then for the displacement subscales on the element boundaries, we are going to simply enforce that we need to have equilibrium of tractions across inter-element boundaries. And by simply enforcing this condition, we are going to obtain this expression for the subscales, which is basically the product of a stabilization parameter times this jump of normal stresses across inter-element boundaries. And this is the expression for the stabilization parameter. So now we have all the models that we need for these subscales, both for the displacements and for the pressure. And we can introduce them in our finite element formulation. And if we do this, the final weak form of the problem is this weak form here. So we have the original terms which have not been highlighted. And the highlighted terms are the terms which come from our variational multiscale formulation. So the thing is that these are a lot of terms and this is expensive to compute, but in fact, what we want is to be able to reach the incompressible limit. Only one of these terms is the one which is required, which is precisely this green term here. So in our finite element formulation, what we are going to do is to discard all of the terms which are in brown here, which are not required for stability, and that's how we are going to solve our finite element problem. But when we go to the error estimator, we are going to keep all of them. Okay? So in the error estimator, we have all of the terms, and in our finite element formulation, we keep only the one which is required for stability in the incompressible limit. So this is the definition precisely of the error estimator. We propose to use as an error estimator a weighted norm of the orthogonal subgrid scales. So we are going to have the addition of the norm of the interior or element interior displacement subscales, the pressure subscales, all of them integrated over the element volume, and then we have the boundary displacement subscales, which is going to be integrated over the element boundaries, and each of these terms is going to be weighted by the appropriate stabilization parameter. We are also going to define an energy norm in order to compare or to assess the performance of the error estimator, which is simply this energy norm here, which accounts for the deviatoric deformation energy plus this norm of the pressure. And then we define, as usual, the error as the difference between the exact solution and the finite element solution. And the nice thing about this error estimator is that we can show that the exact error is bounded precisely by this norm of the error, and also that it is quite convenient to use this definition of the subscales space, so the orthogonal space to the finite element space, because the error bound is sharper if we use this definition of the space for the subgrid scales. So let me just show some analytical examples which illustrate how this error estimator performs. In this case, we have a divergence-free solution for a compressible material. The nice thing about this solution is that only the subscales on the element boundaries are active because the other ones are zero. And then here we are comparing the energy norm of the error and the error estimator. We can see that the distribution of the error is quite similar. And then if we integrate this energy norm error over the complete computational domain, and we do the same for the error estimator, and we compute the global efficiency, we can see that the global efficiency is quite similar, is quite close to 1, so this is good results. This is a second hydrostatic solution for an incompressible material. In this case, only the displacement subscales on the element interiors are active. And again, we do a good job in approximating the exact energy norm error with our error estimator. And again, the energy efficiency is quite close to 1, not as close as in the previous case, but quite close to 1. The final analytical solution is an hydrostatic solution for a compressible material. In this case, only the pressure subscales are active. And again, a good comparison here and an efficiency index which is close to 1. So we also test the performance of the error estimator in an analytical singular solution. And in this case, we can see that we are able to very well capture the singularity here. So our adaptive mesh refinement process effectively refines at this area here. And then we obtain the expected superconvergent result. So we also wanted to extend our error estimator to more interesting settings. So we wanted to extend this to the nonlinear problems, and in particular to damage problems. So in this case, we are using a nonlinear damage model. And we are using our mixed UP formulation, which allows us to reach the incompressible limit with an additional ingredient, which is the smoothing of the strains before we enter to the constitutive equation. And this has been proven to be an important ingredient because with this smoothing of the strains, we obtain a formulation in which when damage appears, the direction of these fracture lines is not going to depend on the alignment of the mesh, but it is going to be completely independent on that alignment. So this is a nice result. And then with respect to the error estimator, we were also quite happy because our error estimator is capable of detecting the apparition of damage and of allowing us to refine precisely in the fracture lines region. And then we extended this to 3D. This is a machinery piece which is fixed in this boundary here, and we apply a loading here. And then, well, as we load it, some damage is going to appear, and then our error estimator is going to allow us to refine this region as expected. Okay? So this is the first ingredient that I wanted to discuss today, and well, it is an efficient error estimator based on the variational multiscale method, which has the advantage of at the same time allowing us to reach the incompressible limit and providing us with an efficient error estimator. The second ingredient I wanted to discuss today is the topology optimization under uncertainties on high-performance computing clusters. So the motivation for this is that, well, large-scale topology optimization, of course, is very interesting from the engineering point of view, but it also poses some challenges. For instance, so with the availability of large-scale computing, we will want to obtain more and more accurate results, so our finite element models will be more and more finer. Also, in topology optimization, we are going to have a large set of design variables, so this is a problem. And then we will need to couple these two ingredients with uncertainty propagation methods if we want to consider complex loading cases, such as stochastic loads and probability, and taking into account probability. So if we want to take all of this into account, we need some tools in order to deal with this. And in our group, we have been working in a series of ingredients which allow us to deal with this type of problems. So the approach that we propose is based on three ingredients. The first one is a parallel sparse grid stochastic collocation method, which will allow us to integrate over the probabilistic space. The second one is classical domain decomposition parallelization, together with hierarchical adaptive mesh refinement and dynamic and efficient dynamic load rebalancing strategy. And finally, in order to couple these two ingredients, we are going to use a two-level parallelization scheme, which enables us to minimize the communication and to exploit the efficiently high-performance computing clusters. So let me start by writing the stochastic problem setting. So we will start by considering a linearized elasticity system, but with the particularity that now external loads can be random, so they are going to belong to a probabilistic distribution. And this means that if we go to our linear elasticity equation, which is this equation here, the solution is not going to depend only on the spatial coordinates x, which belong to a spatial domain D, but they are also going to depend on which is the probabilistic event that we are considering. So we are going to have these probabilistic coordinates omega, which will belong to the probabilistic space capital omega. Okay? And we need to take this into account. Also, we want to solve a topology optimization problem. So the thing is that we do not want our full and complete computational domain to be filled with a material, but we want to avoid the usage of too much material. So we want to optimize the collocation of this material. So what we are going to do is to consider a constitutive equation in which we take into account the presence of two types of materials, a stiff material, which is this material here, and a soft material, which will account for the void, which is going to be this material here. So in our constitutive equation, which is the usual one, so these are the stresses, which are represented as the constitutive tensor times the strains. This constitutive tensor is going to be computed as a linear combination of the stiff material constitutive tensor plus the soft material constitutive tensor, weighted by this density function here, which is going to be 1 in the stiff material area and 0 in the soft material area. Okay. So now we want to solve the topology optimization problem associated to this problem, and in particular we are going to try to minimize the compliance, which means that we are going to try to minimize the work done by external forces when we apply them on our structure. And this minimization is going to be subject to two conditions. The first one is that the linear elasticity equations need to be fulfilled for any random event, of course. And the second one is that we will have a limited volume fraction for the stiff material, so only maybe 30% or 40% of the total material can be effective stiff material. So this is the topology optimization problem in a deterministic setting, but as I was telling you, we can also consider the presence, we want to deal with the presence of loads which are not deterministic, which are stochastic. And in order to do this, we need to write down the robust topology optimization problem. And in this case, we are not going to try to minimize the compliance, but we are going to try to minimize the addition of the mean value of the compliance or the expectancy of the compliance plus some weighting coefficient times the standard deviation of the compliance. And this, again, will be subject to the fulfillment of the elasticity equations at any random event point and also to the volume fraction restriction. But the important point here is that computing this and minimizing this mean value of the compliance and its variance will involve an integral over the complete probabilistic space. And this, of course, is going to make things much more expensive, okay, from the computational point of view. So this is the problem that we want to solve, and now I'm going to explain which are the ingredients that we have been using in order to solve it. In order to optimize this problem, we are going to rely on the concept of the topological derivative. And the idea is very simple. The topological derivative is simply a measure of the variation in the total global compliance due to the switch at a point from a stiff to a soft material, or vice versa. So for instance, in this point here, we are going to see what happens with the total compliance if at this point I switch from the stiff to the soft material. So this topological derivative, in the case of the compliance, it has an analytical expression, and for deterministic problems, it is this expression here, which is quite simple. It is simply the product of the stress tensor times a polarization tensor, which is very easy to compute, times the strains. Okay, and this is the topological derivative for a deterministic problem. But if we are in a stochastic setting and we want to take into account probability, we will need to integrate this expression over the full probabilistic space, and also we are going to have to multiply it by these terms here, which involve the expectancy of the compliance, the variance of the compliance, and the compliance itself. Okay? So this topological derivative here has some nice properties. So for instance, it can be shown that it is positive at any point which belongs to the stiff domain, and it is negative at any point which belongs to the soft domain. And this property allows us to define a sign topological derivative, which is simply obtained by changing the sign of this topological derivative here when we are in the soft domain. So this sign topological derivative is positive everywhere. And with this sign topological derivative, we can define the following optimality criteria. So this optimality criteria tells us that if we are in the optimal solution, in any point of the stiff domain, the value of this sign topological derivative is going to be larger than the sign topological derivative at any point of the soft domain. Okay, so this is our optimality criteria. If we fulfill this, we are at the optimal solution, or at an optimal solution, because this is a heavily nonlinear problem. So the only ingredient that is missing now is to define the volume restriction enforcement, and in order to do this, we are going to rely on a level set function, which is this psi function here, which is obtained simply by adding to the sign topological derivative a scalar or a Lagrange multiplier, which will be in charge of enforcing the volume restriction. And this level set function, as usual in level set methodologies, will define which is the region which is occupied by the stiff domain and which is the region which is occupied by the soft material. Okay. So another ingredient that we still lack is a methodology in order to integrate over the stochastic domain. So we will need to use a quadrature rule in the probabilistic space, because in order to compute the expectancy, so we will need, for instance, to integrate the compliance over the probabilistic space, and similar thing will need to be done with the variance. And in order to do this, we are going to work with a multidimensional collocation point method, which is used in order to approximate these integrals, and basically it will allow us to integrate over the computational domain in an efficient manner. With respect to the refinement criteria, we are going to use a very simple refinement criteria here, which will consist precisely in refining only a series of layers of elements which are close to the interface between the soft and the stiff material. And also we are going to start our simulation with very coarse meshes, and then as we approach the optimal solution, we are going to start refining. Okay? And also we are currently working on combining the geometrical criteria with the variational multiscale error estimator that I just explained, but I cannot show the results yet. Okay? Okay, so this is the simulation process. So we start with a very coarse mesh, and then as we approach the optimal solution, we will start refining our mesh in the area which is close to the interface, and this is going to allow us to capture with a lot of accuracy the geometrical properties of the topology. So the final ingredient in order to solve this problem is a two-level parallelization scheme. So as you can imagine, solving one of these problems can be quite expensive, because apart from having our finite element simulations, we need to integrate over the probability space, and we need to solve a lot of simulations in order to do this. So in order to approach this problem, what we do is to provide our methodology with a two-level parallelization scheme. The first parallelization level is a parallelization at the stochastic point. So at each iteration of our topology optimization process, what we are going to do is to solve a simulation in each of the stochastic collocation points, and this is the first level of parallelism. So in our supercomputer, we are going to parallelize this. But at the same time, each of these processes is going to, in which we solve a finite element simulation, then in here we are going to use a domain decomposition approach with adaptive mesh refinement. Okay? And then if we take a look at the MPI setting, because we are going to solve this in distributed memory machines, so we will have two sets of communicators. The first one is going to be at the domain decomposition level in each of these stochastic points, but at the same time, each of these subdomains is going to be communicated by to the same subdomain in other stochastic collocation nodes. Okay, so that's the main idea. So we started with the validation of the problem by using a Michelltype structure problem, which is this structure here. And then we have three loads here which have exactly the same mean value, but the variance in this load here is much larger. So if we use a deterministic approach to solve the problem, we arrive to a quite symmetric solution, as expected. But if we take into account the probability density function, we arrive to this solution here, which is much stiffer in this area here due to the large variance we have here. And then if we take a look at our adaptive mesh refinement meshes, we see that we have been able to very heavily refine in the area which is close to the interface between the stiff and the soft material. So we can capture very well the definition of the geometry at these areas here. But at the same time, the computational cost for this was not too large, because we concentrate all the computational effort in this area here. If we now go to the supercomputer and we check at the parallel scalability, so we can see that, okay, if we study the strong scalability of our methodology for a deterministic problem, and we only introduce parallelism at the domain decomposition level, then at something which is close to 200 processors, scalability is going to begin to be not so good, because the size of the domains is going to be very small, so then we are going to lose performance here. But if we combine the two-level parallelization scheme and we allow to do parallelization at the stochastic and at the domain decomposition level, then we can obtain much nicer results with good scalability up to 2,000 processors. And finally, this is a weak scalability plot. So in this case, the optimal plot here would be a flat line. And then again, if we study the weak scalability of with parallelism only at the stochastic level, we obtain this line here. So Scalability is quite good up to 2,000 processors, but beyond that, the curve is going to explode. But then again, if we explode at the same time the domain decomposition parallelism with the stochastic parallelism, we can obtain very nice scalability up to 20,000 processors. And as a final example, I will show a large-scale simulation. So this is the robust topology optimization of an airplane bearing bracket, which is subject to random loading. The resulting finite element meshes are adaptively refined, and they have between 75 and 120 million elements, and simulations were run by using up to 1,500 processors. Okay? So these are the results for a volume fraction of 50%, and we can see how our adaptive mesh refinement allows us to capture a lot of details of the geometry of the resulting topology. These are the results for a volume fraction of 20% with more details here. And finally, these are the results for a volume fraction of 10% where we obtain very slender structures here. And if we take a look at the details, we were quite happy because we obtained these bone-like structures which are structurally optimized for this random loading. Okay, so, and then let me finalize by very shortly talking about variational multiscale reduced order models. The idea is that now we want to extend our capabilities to deal with fluid structure interaction problems. And in fluid structure interaction problems, what we are going to find is that at each of our iterations of the topology optimization process, we will need to solve a complex fluid structure interaction, which possibly involves also turbulence. Okay? So, as you can guess, the computational cost of this operation is going to be very large. And in general, the fluid mechanics simulation is going to be much more expensive than the solid mechanics one because of turbulence. So we need to develop some strategy in order to try to reduce this computational cost, at least in intermediate simulations of the optimization process. And one possibility to do this are reduced order models, which can be useful in this setting. So in our group, we have been working on reduced order models for some time, and in particular, we have been working in both proper orthogonal decomposition approaches, and more recently also in finite elements adaptivity and artificial neural networks. Okay? In both of these approaches, we have realized that a very important point when you try to apply these reduced order models to fluid mechanics problems is that we need to take into account a closure model, because the nature of the problem is highly unstable, and if we do not take into account a stabilization or closure model, the reduced order model is not going to perform properly. So today I'm not going to have too much time for this, but let me simply summarize the idea on this. So the idea of any reduced order model is to project our full order model, the high fidelity model, onto a reduced order subspace. And in particular, so if you use POD, you are going to express your solution as the linear combination of several reduced order basis functions times some reduced order coefficients plus possibly a mean value. And if you're doing POD, the way to obtain these reduced order basis functions is by collecting several snapshots, by solving a full order problem, then performing a singular value decomposition, and keeping only the most relevant reduced basis functions. Okay? Then the reduced order system is this system here, which is this A phi here, which is simply obtained by pre and post multiplying your reduced order, your full order matrix by the reduced order basis. Okay? And then if we use a Galerkin projection, the final reduced order system is this reduced order system here. For non-symmetric problems, we would probably use a Petrov-Galerkin approximation, but I will do the development on this model here. So what we realize is that this model is not enough, because we need to take into account the discarded modes in our reduced order model. And for this, we need a closure model. So the idea is the following. We are going to define the exact solution, so the high fidelity solution, which can be obtained by inverting this linear system here and applying it to the right-hand side. But now we realize that this full order solution, so the high fidelity solution, can be decomposed precisely into the projection of the full order solution onto the reduced order subspace, plus something which cannot be modeled by the reduced order subspace. Okay? So this is a similar decomposition to what we do in the variational multiscale method, and what we are working on is precisely on building a model for the effect of the subscales here in our reduced order model. So now in our reduced order model, we are going to have the contribution of the original system plus something which takes into account the effect of the discarded modes. And I will, in general, this term is not going to be zero, so it needs to be taken into account. And I will, well, if you do not take it into account, you unstabilize your problem. And I will not have time to explain it today, but I refer you to Alexis Tello's talk on Wednesday in room Levant 2, where he is going to show some results for these variational multiscale reduced order models in fluid structure interaction problems. But before I finish, let me just show an example of why this is important, an example on which this was really important. So this is a backward-facing step problem with a Reynolds number of 37,000. So it is a 2D example. The flow is not too complex, but anyway, the flow is a bit complicated in this area here where the vortexes are appearing. So if we now try to solve this by using a proper orthogonal decomposition method, and we use maybe 35 degrees of freedom or 80 degrees of freedom, so this is a comparison of the solution of the full order model, which is in blue, the reduced order model with 35 degrees of freedom, which is in red, and the reduced order model with 80 degrees of freedom, which is in black. So we can see that even if we use 80 degrees of freedom, the solution, the accuracy of the solution is not going to improve. And it is not going to improve because if we want to properly capture it, we will need a lot more of degrees of freedom. Okay? On the contrary, if we take into account the effect of the discarded modes and we use our 35 degrees of freedom reduced order model, but taking into account the effect of the discarded modes by means of a variational multiscale method, we obtain these results here. So in this case, the green line, which is the reduced order model with the subscales, is much closer to the solution of the full order model. And the nice thing is that if we take a look at the spectra here, so we can see that this is the spectra for the reduced order model without the subscales. In blue, we have the reduced order model and the full order model, so the high fidelity model. And then in green is the reduced order model with the subscales. So the subscales are effectively capable of diminishing the energy of the high frequency modes, which was too large in the original reduced order model. Okay? Okay, so in order to conclude my talk, let me just say that topology optimization of structures is a challenging matter, which especially if we are trying to deal with complex loading cases such as stochastic loads or fluid structure interaction. But then we can deal with it with the combination of several techniques which can help alleviate these problems, which are the usage of parallel adaptive techniques, efficient error estimators, multi-level parallelization schemes for robust optimization, and the usage of reduced order models in the fluid structure interaction during the optimization process. So thank you very much for your attention.